Well, thank you for the great introduction, and also thank you for inviting me. It's really exciting to see that there are more people than I thought would join being interested in I/O. As Georg already mentioned, I have a very diverse background today when it comes to research, but I started out in network and I/O research originally. So this is still one of the things that is very close to my heart. And today I'm trying to capture activities that my group and people I have been collaborating with over the last couple of years have been working on to provide better insight, understanding about I/O and HPC systems. And this may not come to you as a surprise, especially if you're interested in HPC, but our systems have become very, very complex from a standpoint of hardware infrastructure, but also software infrastructure. We see very heterogeneous system architectures, a very diverse mix of components, including storage components. And at the same time, we have seen a rise in new computational paradigms. We see new parameters that become important when it comes to system tuning. And at this point, we have come to a stage where, especially for humans, optimally and fully understanding the full picture is almost impossible. Still, specifically for I/O, we do need experts to tweak and look into applications. And what my group is really targeting is trying to help with improving the accessibility of insights and knowledge about how your application is behaving and how a system is behaving. So it all comes down to we're seeing more and more heterogeneous and complex infrastructures. At the same time, we've seen a shift in the way workloads are being deployed on HPC systems. Specifically, if I look back into my own career, when I started as a PhD student working in the I/O topic, that was like in 2014, 2015. It was mostly dominated by what we call today traditional HPC, meaning we had very bulk synchronous I/O phases, oftentimes write or read phases, mostly targeting checkpoint and restart files or simulation workloads. And that was something, even though it was already pretty complex to optimize and understand, it was somewhat well understood and our tools were mostly in place. But especially if you're attending different conferences, you've seen that we see a much more diverse mix of HPC workloads today, specifically what we call emerging HPC workloads. And there you have anything starting with machine learning, big data analytics, multi-step workflows, up to deep learning and artificial intelligence being deployed and run on HPC systems today. To give you a better understanding on how popular machine learning has become in recent years, this is a study that has been performed on the Summit supercomputer in Oak Ridge, and it was published 3 years ago. And they looked into different science domains and what kind of methodologies they're using to accelerate their jobs. And the interesting part was that almost all of the jobs that use some form of machine learning to accelerate their code. And at the same time, the breakdown was basically any science domain being run on the system was using machine learning at that point, meaning that the optimizations that had been performed up to the point that Summit had been deployed became not ideal anymore for the picture, basically the big picture of workload mix that you see today. And that's where we start with the main motivation for the work that I'm really interested in. We see very different I/O today, and the performance characteristics of all of them are very different, meaning that today HPC I/O is more than just checkpointing and bulk synchronous parallel I/O. And with that in mind, this is one of the motivations where I think we should drive the definition of understanding and observability. Because again, HPC is no longer just what we used to call HPC 10 years ago. We see very complex workflows with very diverse characteristics. We have new questions that arise today when you run your workflows, oftentimes meaning that the tools we have been using so far may not be sufficient to answer your questions anymore. Specifically, if you look into performance variability for workflows, new interfaces, new libraries, new programming models becomes more and more difficult. And specifically for I/O, it's even worse because we're still lagging behind in the sense of just creating tools or extending existing tools to a point that we can understand performance meaningfully. meaning that we're at a point where monitoring is not observability anymore, because monitoring oftentimes gives us what happened in some form of aggregated way, but oftentimes it does not give us why it happened and what we should do. What we need is basically context of IO operations to get closer to what we call the explainability initiative. And this is basically the baseline. Again, why is IO so complex? When I started as a PhD student, we were very much limited to the left side of this figure, and DAOs was not even in the picture yet. We had our traditional parallel I/O stack, we had our parallel file system sitting on top of HDDs and SSDs, we had our I/O forwarding layer back then, our low-level I/O libraries, some high-level I/O libraries, including, for example, HDF5 and parallel NetCDF. In between, we had MPI/IO, oftentimes serving as a bridge between high level and low level, and on top, our applications. We have now outgrown this picture. And again, I cannot put every single paradigm that is out there today in this, because otherwise we couldn't even see what's on the slide. But we've seen a growth when it comes, for example, to architectures. We're not only seeing parallel file systems anymore. We're now moving beyond that, including object store, cloud store, and maybe many different forms of storage architectures in the future. And at the same time, the stack and the interfaces being used and the frameworks being used have been changing as well, including, for example, TensorFlow, PyTorch. We see virtual machine deployments. We see different forms of storage layers we're interacting with. And at the same time, the hardware has also become more and more diverse in the sense of the hardware technology available, but also the way it's being deployed on systems, leading to numerous factors that you have to consider when you look into I/O, because I/O essentially on an HPC system is some form of communication in the sense that you're using the shared network to access data, be it reading or writing the data, while at the same time other applications may use the network. And there are so many different factors that then can interfere with the performance you're observing. And if you look into the current status of I/O characterization tools, I picked one of the most famous ones because it is today one of the most widely used when it comes to I/O monitoring on a global scale. My research collaborators and I would talk to many, many people, and this was basically what would be used if they're looking into I/O. And the way Darshan reports I/O is typically by recording when did the write or read start, how many bytes were written or read, what kind of interfaces were being used, and it creates a specific type of log format that gives you an idea of what kind of I/O has been performed for the application, but it comes with some design flaws in its current state. For example, you cannot really connect from an aggregated Darshan log what job it related to. So identifying, for example, if you observed all of the jobs on the system or only a fraction becomes difficult. And that's an interesting problem because, and I was similarly naive until 2 years ago, I thought, yeah, great, let's just use Darshan logs, right? There are sources available. There are specifically 3 popular logs or log sources that are still being used for research when it comes to optimization or looking into future system design. And then a friend of mine pointed out, but you do know that you cannot tell whether these logs have been complete. And the reason he raised this question was he worked at Argonne for some time, and he talked to a lot of the users there. And they told him basically, if we see any problem with the I/O, we'll look into any environment variable we're not familiar with and disable it, resulting in Darshan oftentimes being not enabled anymore, so they wouldn't be included in the aggregated logs. So the main core question that arose was how relevant are those logs then to current systems? And is research being performed with these logs even relevant? And that was basically the spark for a long discussion that also led into looking into different tools and different categories of tools. And that's an interesting observation. If you look at the available tools, there's so many great tools out there. For example, if you come from the application level, Darshan is a go-to tool. We also have tools such as ScoreP or Recorder. They provide you some form of fine-grained function tracing, but at the same time, they have very limited or no visibility into the system. Then you have system-level tools such as LDMS or TechStats. They provide aggregated I/O performance metrics, but at the same time cannot really correlate with what is happening in the application spectrum. And then you do have quite some end-to-end tools available that try to provide a holistic view, but at the same time, because they have to compromise when it comes to overhead, they don't provide deep profiling and deep view. And that results in a quite interesting observation. You have basically siloed tool views. Each tool is dedicated to a specific layer, but explaining specific events observed in different tools is oftentimes not easy to connect with each other. Another thing that is specifically with regard to, for example, reproducibility, or just the fact to be able to repeat experiments, you oftentimes see very customized workflow scripts dedicated to specific experiments, which can sometimes result in unscalable or unrepeatable scripts. And it's even worse if you look into different benchmarking tools. Sometimes they require different formats or logic that is not even compatible with, for example, your batch system. And that results in something what we consider as discarded insights, because oftentimes performance optimizations or studies are done multiple times on very similar problems, but not kept or reused for future efforts. Unless you're talking to very trained user groups, in the sense of user support groups, they oftentimes have this vast knowledge. But if you're just coming in as a new user or a user who hasn't access to great user support, you may not be able to tell that this research you're looking for is there. And that's also a motivating factor that we're trying to include. So what is basically happening right now? If you look into observability versus I/O performance variability, we do have tools, again, as mentioned, that provide it to some extent what was happening for a given layer. And I have highlighted those layers in the stack. You see it's the traditional I/O stack, if you want to say so, but laying on the side. And the turquoise greenish boxes are insights that we can gain from current tools. But there's so many other things that would be interesting where you have very limited access to, oftentimes because overhead can become a challenge. And these are interesting layers in the sense of, for example, especially in the kernel, there's so many things happening on the system side that can result specifically in variability that you as a user will never be able to tell. And maybe it's not even your application, but the system as at a given point in time. And so this is something we have tried to keep in mind when we were working on all the different, or are still working on different solutions. Where do we want to go? Traces are a blessing and a curse at the same time, because if you trace applications, the larger your application run, the more difficult it becomes to do a fine-grained tracing, just because the overhead and the log files associated with it just exceed too much space, basically. But at the same time, we do need trace and data-driven methodologies to get a better understanding of what's happening in the system. And so a vision that started as a scribble on a napkin, I think, a couple of years ago, and is now something quite a few people are trying to push, is instead of creating a new tool, and create some framework that is able to capture all the amazing things that are happening, basically using benchmarks and tools available today. And what we would like to see, and this is basically something we're working towards to, but that we do not have in place yet, is some form of performance history database, or if you want to say so, training set over many different systems for many different applications, basically categorizing their behavior and characteristic patterns for different science applications to just have the training set you would need in order to train AI models capable of trying to solve what we're trying to do here. So this is the goal we have in mind. But at the same time, we're trying to spin the traditional performance cycle in an automated fashion, holistically at the same time trying to keep track of all the different things that are happening. And this is basically where we want to go to. We do not have this tool. It would be amazing if we would have this tool, but we have some steps in place. The idea behind is no matter if you're running simulations, applications, benchmarks, collect information with low overhead or as low overhead as possible. Use different tools, existing tools, ideally tools that are very popular already in the sense of they are being deployed right now by HPC sites. So we don't have to convince them that they should use tool X, Y instead of the tool that they have already employed, and at the same time capture system metrics. And there are many great tools in place that do that already. We're trying to spin the cycle, basically, and then include monitoring from a job and a node level and push all of this in a history database. This is also motivated by the fact that we have a couple of different use cases we would like to see driven even further than they are being driven today, in a sense of enabling optimization, but also performance prediction, ideally even workload generation for realistic simulation tools, meaning writing simulators that can then use these inputs to provide meaningful insights instead of using a Darshan log that may be 10 years old. And that may need additional metadata derived from the information collected, but ideally being preserved so that others can use the knowledge as well. So this is basically trying to close the observability loop. And we have done some interesting projects, and I'll just dive into the work we have been doing so far. So one of the more recent work, and that's collaboration with Lawrence Livermore, and one of my PhD students has been working with Lawrence Livermore for almost 1.5 years now, is looking into verifying performance beyond the traditional metrics. And that is an interesting problem because we didn't even consider this until we had a very in-depth conversation about this problem. We call it Verify I/O. So this is not targeting I/O operations per second or I/O bandwidth or I/O latency, jitter, you name it. This is specifically looking into consistency semantics for parallel I/O. And now you may be like, why should I even care about this? This sounds boring. Well, what we came to realize is that if you move beyond the traditional POSIX consistency model, basically into a more relaxed consistency, be it from MPIO, session, or any other format, your application that may have been performing correctly on a system today can break in the future because it's not adhering to consistency semantics. So this is an important tool in the sense you can ensure correctness, even for relaxed consistencies. You can diagnose portability issues, specifically when you want to use your application deployed on another system. You can look into the support of your application if we ever move really beyond true POSIX. And this is also something that can help developers, for example, and people maintaining the standards, different forums, for example, to detect and fix semantic violations and improve standards as we have them today. And the idea behind it is very simple. First, you generate a trace of your application, and we use Recorder Plus for this, which is an extended version of the traditional recorder tool. Then we build conflict groups. In the next step, build a happens before graph, and then verify the consistency. And you can see a simpler representation of this here. But I want to walk you through a tiny example. So what we do first is we run our code with Recorder again, and for simplicity, I have selected a smaller MPI program. Otherwise, I wouldn't have been able to fit it on a slide. But in the first step, you build a happens before graph from the trace that you have generated. So you run your application with Recorder Plus, and from there, you basically reconstruct with Verify.io the program order and the synchronization order observed by your application. And by performing this and combining this information, you build the happen before graph or happens before graph, which basically captures the causal relationship among different operations. And this is important in order to detect the consistency semantic violations. In the next step, you scan your trace or your graph basically to find the conflicting operations and build pairs. And two operations conflict if they access overlapping file regions, or at least one of them is writing onto the same file at the same time. This, for example, also includes handling offsets properly. For example, specifically when APIs do not expose them directly. Example could be fwrite needs to be resolved with preceding lseek. And the result is basically what you see here in the middle. You have a conflict, pairs, or groups. And then the next step, you select the consistency model you're interested in and basically do a step-by-step check for every single pair. Meaning that for each conflict or potential conflict, you check if it is properly synchronized for the targeted model, POSIX, commit, MPIO. And this is basically done by checking whether the reproducibility is given in the happens before graph. Meaning if there is an appropriate path, for example, containing the needed sync operations between, for example, MPI file sync, then the conflict is synchronized and we're good to go. If it is not, then it is flagged as a data race. And this is basically for pair 1, we're good to go. For pair 2, the path is given as well, but for pair 3, you see that the path is missing, and this is a potential data race because in this specific example, we do have a foo text file that is being read and written to in an unsynchronized manner with the same offset. And all of this can basically be reduced to a graph reproducibility problem where you ask that given for 2 nodes, and nodes means conflicting operations, if a valid synchronization path exists. If yes, then we're safe. If the answer is no, then we have a potential data race. And in this specific work that we just recently published, we tested different algorithms that can be used to solve this problem and tried out their performance against each other and optimized and tweaked a little bit. And you can look into the code if you're interested too. It's open source and available. We did some really interesting test study with this as well, because we wanted to know, what do people do when it comes to consistency semantics? So we used Verify.io initially with 91 built-in test programs from different I/O libraries, high-level I/O libraries, including HDF5, NetCDF, and ParallelNetCDF. And we checked it for 4 given consistency models. And the core question that we wanted to know is, do these I/O libraries comply with the current MPI standard as is? And what you can see in the table here is basically the number of test programs available are being provided with these libraries, and the number of programs with potential data races the moment we go beyond the traditional POSIX consistency that we could identify. And you see it is a fairly high number of programs, even in the test code, that is oftentimes used by new users to then adapt their code to a new high-level I/O library, that knowingly oftentimes, because we talk to the developers, violate the current MPI standard for performance reasons. But at the same time, this means that whenever you move beyond traditional POSIX consistency, your application could easily break and is not portable to the new system. We identified a couple of test cases where only the library implementation had consistency bugs, but surprisingly though, for ParallelNetCDF, the same tool was able to identify even communication bugs in the library itself. And here you see, again, an overview of all the different test cases that we looked into. And this is basically a heat map representation of where consistency semantics were violated for a given function. We have reached out to the MPI forum and have proposed 2 new I/O synchronization APIs so that we can help fix this issue, so that in the future, whenever we move beyond traditional POSIX, applications may not break, even though they may have followed given test programs. So this is one of the things where we think traces and data-driven insights can be really helpful to identify how your application is behaving beyond the traditional I/O metrics. Based on this work, using Recorder Plus and even updating Recorder Plus at this point, we have one work in progress where we use a similar approach of collecting traces, but at the same time see it more like a sandbox for what-if analysis. So beyond the traditional skeleton, the I/O skeleton you may have known from research that has been published 10 years ago, or even longer ago, this is not purely meant as an I/O benchmark tool where you can create an I/O kernel from a given application, but this is meant as a tool that can help you describe your application pattern. And the idea is that we want to move beyond the traditional I/O bounding box approach that was introduced by Redefining with the I/O 500 more towards do we need some form of individual bounding box depending on a given I/O pattern for a given system? Because an I/O pattern may determine the maximum of performance that can be attained by an application. And at the same time, we want to be able to use this tool to reproduce original I/O performance. So it is basically also meant as a test tool, but at the same time expose optimization to be able, for example, to tweak parameters, for example, for your MPI application. And it is very similar to what we've seen just now. You take traces, you filter the trace, create your context-free grammars, compress it. From there, you derive the I/O behavior, which then creates your benchmark. And the last step, this is basically what we're currently working on, which is why I can't show you any results yet, is step 3 and 4, where you have an automated loop to even test it in a what-if and replay form. But then we thought this is not good enough yet, because this is still very close to what people have been doing so far. So we moved beyond, and what we're now looking into is how can you get a better observability inside the kernel without creating a tremendous overhead for the application. And a very popular approach that has been used by networking tools for a very long time is using eBPF. It has become fairly popular with the I/O community at this point as well. And the idea is by creating a bridge between traditional tools such as Darshan and LDMS, we are able to close the gap in explainability and help answer the why, not just the what happened to an I/O operation. And initially, we were fairly optimistic because you attach your eBPF probes to the user application middleware, and if possible to kernel components as well, to basically get the full end-to-end picture. But if you just run it as is, even one single write to your local machine can create a tremendous amount of overhead. So we had to do some engineering work here and some research. We talked to machine learning experts and identified the performance relevant hooks, which resulted in less than 20, surprisingly, that make up of around 95% of the performance. And we're now able to basically provide insight into what happens in the kernel. You can visualize what's happening with Perfecto and just observe your application that is running, but you can also use the data that we're creating to create specific breakdowns of performance. And that's what I'm showing here. This is some initial work that we've done so far, where we just looked into different write and read modi and looked at how those impacted the actual write or read performance. We also did a fairly interesting comparison study between Darshan DXT and Datacrums. And what you can see here is that even though we only have overhead of approximately maybe 1.2%, we're able to get a fairly accurate overview of what is happening when you perform a write. So for example, you can see that here a lot of the time is spent in balancing the dirty pages or in calculating the X4 inode checksum. For the buffered read, you see that the file map get read batch is the function that is using most of the runtime. And then specifically, if it can be served from OS patch caches, we were able to identify how page cache faults, for example, and misses result in higher latencies in that sense, and impacting performance to a point where you see observability even on an application level that can explain why sometimes your application performs better or not, independently of what is happening on the system, which is fairly interesting. And then this is also an interesting breakdown with Darshan, for example. If you write onto an existing page on X4, you know how long the writing took and how much has been written, like how many bytes have been written. But at the same time, you lack any perspective on where the time was lost. And with Datacrums, we were able to showcase, okay, this is how much time is being spent in the X4 actual write. Then we have the actual write begin and end operation. While, for example, if you write to a page that results in evict and reallocate off a new page or in the page cache, then you see that the same amount of time is spent in the breakdown as before. But in addition, you have the file modified time that is being introduced because you have the eviction of the page and allocation of a new page. So very cool thing. We're really excited to look into this even further to better understand what is happening on a parallel spectrum. So all of this is highly specific, but all of these are trace and log file-based methodologies that we want to incorporate even further, specifically with reproducibility and explainability in mind. So what I want to move next is basically how do we use trace-based work, your own work, this work you're interested in, to improve reproducibility and, even more important, trust in benchmarking. And I'm not talking about benchmarking, I'm talking about benchmarking. First thing you need to understand is that terminology is not clear. It's surprising when you talk to 4 different people, all of them may have a different understanding of what reproducibility even means. In its truest form, if you go by definition, you should be able to document your results in a form that if you can create identical system settings and system state, you should be able to get identical results. Now, if you run a code on HPC systems, that is a tough challenge because you cannot really influence what other users are doing at the same time. And you cannot force every single user basically to run the same code at the same time again. So we do see different variations. Sometimes it's called replicability, where it's more like reproducing the findings by independent researchers. You have repeatability, which means using the same experimental tools, same observers, same measurement instruments, resulting with the same conditions. And something that I think is a very good understanding of this, and this was also reinforced by Thorsten Höfler in a talk of his, and I think maybe 3-4 years ago, he was really much vouching for reproducibility should be more understood as interpretability, meaning that if we have enough information, basically metadata available, scientists should be able to understand the experiment, draw their own conclusions, and be able to generalize the results by rerunning experiments on their system with their test conditions. Having this in mind, This is something we have incorporated. So we have our trace-based solutions. And what we're working on now is moving beyond just looking into traces in a very specific way, meaning running them individually, looking into the results. We're trying to combine benchmarking and reproducibility, which sometimes can be a challenge because benchmarking in itself would call for standardized tests, and you'd be surprised how different tests can be. And at the same time, you want to document everything well enough to ensure interpretability, which resulted in key principles that we're trying to reinforce with our work, leading to we need to be able to record the hardware and software configurations, test settings, data in an easy way, meaning that it is not prone to error too much. We need to be able to have version control, to be able to check for consistent test suites and tools when we rerun our tests. Ideally, we have some form of automation to minimize the human error, which can be a real problem. We are trying to look into the standardization, specifically industry standards of benchmarks and metrics, which is surprisingly not well maintained if you look into very popular community benchmarks. And ideally, you need to perform multiple runs to verify results. And putting all of this together, we have proposed 3 core elements that are key to reproducible benchmarking, if you want to say so. That's being able to repeat without the human error, be able to compare, meaning we need some standardized test loop forms that allow even to compare results across models and methods. And third, we need modularity, meaning that depending on how software develops, how architectures change, we need to be able to incorporate those changes. So in its heart, we have 3 core components: benchmarking, reproducibility, explainability. Basically, be able to compare system performance using standard tests, ensure results are repeatable on same or similar systems, and understand why performance varies and detect hidden issues. We have proposed a benchmarking workflow for this, where we automate specific steps. So the most critical part is that whoever is running this needs to select a performance model that targets whatever they're interested in. And then the rest depends on the benchmark and the metric identification in a sense of what matches the model or the problem we're looking for. And the rest is being driven in an automated fashion. So far, we have been relying on the Joop tool, which has been proposed and maintained by the Jülich Supercomputing Center. At the same time, we did a reproducibility study on popular community benchmarks, and we identified a typical benchmark loop structure, but at the same time, we identified that a lot of the community tools nowadays being used to compare either communication flows or even I/O are more some form of benchmarking, if you want to say so, depending on where they put the timestamps. And that becomes a problem if you're trying to reproduce or incorporate performance insights into your application, if the actual benchmarking loop does not reflect the results that you can observe if you're running a real application. So this is something we proposed, and this is basically the core of our work that ties in together with the vision of holistic performance modeling and performance insights, because key is the way you basically build those workflows and minimize error, while at the same time creating the metadata. And if you're, for example, using tools such as Joop, the metadata needed to document what you have been doing and to basically port it to another system are being given by the framework you're using. We have also played with different models, and I won't dive into the roofline characterization because I think that's probably pretty well known. We've seen some recent work that was really exciting at SC, where they used the traditional roofline beyond your node performance, looking into actual workflow roofline modeling for end-to-end application performance, where you could then differentiate between the node performance bound and the system parallelism bound and the system performance bound, which was really interesting and cool. We did something similar for I/O. We tried to drive the traditional roofline beyond compute problems and memory problems, looking into I/O characterization. So far, we have been using I/O operations per second and I/O bandwidth as the parameters of interest. And we define, instead of the arithmetic intensity, the operational intensity for I/O, which is total I/O operations divided by read bytes and write bytes. And then for the y-axis, you get the minimum between the peak I/O operations per second compared with the peak I/O bandwidth times your operational intensity. And again, because human error can lead to skewed results, we created an automated workflow similar to the one shown on the previous slides, adhering to our reproducible benchmarking design guideline, say so, which we call RT4IO. which then extracts from Darshan logs at this point and from recorder results and generates a roofline visualization for your given problem for I/O. We have driven this even further and now incorporate ML-driven performance analytics into this whole workflow as well. So you do have the full metadata chain, including the description of your experiments. And as the final step, you can then use in the same workflow different machine learning models to look into different case studies. We have performed an initial case study for compute-bound problems, but also I/O prediction, which was pretty cool. The idea is to take the traditional machine learning or deep learning cycle and map it onto an automated flow. And we put it in context of the Jube runtime environment, because again, this has been a framework that we have been using for some time. It is based on XML files. It's pretty straightforward, and you can then have everything in one script, basically, that can then be automated and run as a whole. The idea behind it is to basically have performance modeling in a faster, reproducible, and accessible way, even for users that may not have had in-depth knowledge with machine learning as so far, which can be an interesting problem, specifically if you talk to researchers and said, oh, we did a regression model because that's what everyone does. And sometimes that's not a good enough reason. The tool itself can be run as part of the actual job run with Jube, or in a post-processing stage, you can run it from the command line as well. And it comes with a command line visualization. Here you can see a representation of 3 different phases, specifically the pre-processing, the training, and the prediction and validation phase. We have excluded one of the 4 screenshots for space constraints. The interesting part, though, is it uses the SQLite ML extension, which means that every single model you can find on a website can be incorporated into your workflow. And we have tested it with quite a few things. The first thing we did, because again, my group is very much IO centered oftentimes, we did an IO bandwidth study, and we did it pretty straightforward. It may be lame to at least IO researchers because we used IOR again. But then again, IOR is powerful in the sense that you can run various different IO patterns and just configure it and keep the metadata information in a sense of the configuration, which is pretty neat. We use 25% of the information as training and 75% as validation. And the idea was we wanted to predict IO bandwidth for a given system. And what we did with JubeML is we basically handled the data cleaning, the splitting, training, validation without any extra scripting. We ran the experiment over 3,000 times to collect detailed bandwidth results over time to basically get the observability. And we're able to predict the bandwidth surprisingly accurate with scores of up to 0.99 and a very minimal error. And the whole process took less than a minute to train and then predict for different system settings once we had the data in place. So that's pretty interesting. And because I'm running out of time and don't want to put you to sleep, I'll just skip through the next couple of slides. We have extended our work even beyond this to now look into much of the emerging workloads. The first work we did is also trace-based. It's H5Bench, basically an HDF5 benchmarking tool for I/O patterns, and extended this with I/O workloads. We use DLIO because it is one of the most versatile benchmarks for I/O when it comes to I/O workloads, and used log VFD to extract the information about the different HDF5 functions and then integrated that into the H5Bench tool. We also compared how, for example, DLIO with PyTorch and TensorFlow for the UNet 3D configuration compared to H5Bench with our extension. And the patterns themselves, even though there are variations depending on the framework you're using, the tool reports them differently. We still see that the actual behavior is fairly similar. Same comes for the actual individual I/O segments. We do see some variation when it comes to I/O time, but it follows an overall trend when it comes to the pattern. And the work was just recently published. So if you're interested, this is a bachelor thesis that was performed at RWTH Aachen. This is all available, and the actual benchmark integration in H5Bench will be merged back into the main branch soon. We already have included a pull request. For my vision and closing, I've showed you a couple of things on how you can derive or push towards deriving insights, different possibilities, trying to close the gap between different tools. And I had some really cool conversations with ISC. People have been working, for example, on connecting Darshan and LDMS, so you can actually get the connection between application and system. And that's something we plan to incorporate in this work next. But why do all this? The vision for me is that we want to get closer to self-aware HPC systems in the sense of enabling resilience, efficiency, but also be able to explain behavior, performance, and based on this, be able to design future systems. And this comes down to, we need this loop of observability, models, and feedback to have some form of self-optimization. In order to get there, we may not need more tools or smarter tools. We just need smarter tool systems that are able to incorporate what has been done so far. And it may require a standardized form of metadata and more cross-layer collaboration, which is also part of my outreach, which is why I think it's cool to be able to speak at events like this. We need to be able to create trust in benchmarking, which we're still not there yet, surprisingly. I'm really curious how you feel about metadata standardization, for example, for trace metadata schemas across tools. I know there have been some efforts before. I know they didn't result in a standard yet, or they resulted in many standards and everyone is doing what they're liking most. The other question is, how do we get from metrics to meaning? We may need new metrics, but how do we get verified insights based on results that we have observed? And that's something we will have to look into in the future as well, looking into correctness verification, performance validation, how can we connect those, and then ultimately result in reproducibility at scale. And with this, I would like to open up the discussion for some questions. Thank you.
So first of all, on your slide 11, you explained something like how your vision is for aggregating data sources. And then to ask provocatively, is the long-term vision to just aggregate as much data as we can from different sources and different tools and then hope for some AI insight in the future? Is that what you're saying here? Because it's like, if you say tool independent, I don't really see how that can happen.
So tool independent in the sense of the systematic behind it. We would like to have a standardized approach to collect the information. We had a really interesting discussion about this before as well, because just collecting data as some form of data hoarder at some point or messy won't make sense in the future because we're running out of storage space eventually. What we're really looking into is what questions do we need to ask to get from the what to the why, and how can we collect the information and then keep it so that in the future we can reuse it meaningfully. And we said tool independent initially because we didn't want to write this whole cycle. This was not meant to be another tool that we write and then you have to deploy the whole tool chain. This was more meant of what we're working on right now is what we would really like to see, for example, for some form of dashboard where you configure the tools that are available on your system, select the insights you're looking for, and then basically generate a standardized script that generates the metadata at the same time to reproduce what you have been doing and puts that forward into a database so that you then can run this. This would be a vision. So in that sense, tool independent, because we are not planning to write a new tool. Datagram, for example, is not meant as a new tool. This is more like a link between two tools that are already in place. It also comes with the downside of needing root access, for example, or at least elevated access. So ideally, we want to collect the information in a form that we are able to derive meaningful insights and may be able to drive AI models in the future, be it for digital twinning or real-time optimization of the system, hence the self-aware HPC system loop we're looking forward to. But no, we cannot keep all the data forever. And one proposal I got 3 weeks ago from Scott Klasky was we should just get rid of files overall and should just drop the notion of files and look more into what the database community has been doing, working with meaningful metadata and description of data instead of dumping everything into files and clouding our systems.
All right. Another question about Verify.io. So slide 19, I think it was. Yeah, that one. So my question is it always possible to detect conflict groups unambiguously? For example, if I do MPIO and I possibly create a conflict by writing from different processes to one file, then the positions to which I write could be computed. So it's for a tool very hard to figure out whether that be a conflict or not.
That's a good question. This is something we're currently looking into. That's why we started with available test applications first. Ideally, we want to be able to resolve those and maybe compute them in real time to be able to pair the conflict groups, because it was surprisingly insightful for us to see that for even the standard tests, honestly, we got so many conflicts already. The actual development work is currently being done by Xiaobin, my PhD student, and Chen Wang from Lawrence Livermore. So I'm happy to defer this question if you're interested under the current status. I know that the second phase of the tool is currently in development. So
one problem that keeps appearing in the computing center environment is that different jobs influence each other, especially in terms of I/O. So a job that will probably not have a problem writing its data to disk might be bottlenecked at some point at 3 a.m. because some other job happens to be writing at the same time. So how can we detect such situations? How can we attribute bottlenecking or throttling, as I would call it, to individual users or in such special situations that may not appear in regular operations, but from time to time, and then you don't know what to do?
So this is actually part of what we see here. And this is also a drawing that was done on a napkin that I preserved from a conference. Data crumbs, the initial idea was to be able to follow basically the data path through the system in a way that we're not overclouding the system with performance monitoring or profiling. And what we're working on right now, and we have gained access and collaborations, and Lawrence Livermore, Argin, and Oak Ridge, they will run our tool. Basically, this tool was specifically meant to be able to identify where do we lose the performance. Is this something that is really occurring through bad programming practices from the user, or is it a performance observation based on what is happening in the system, for example, because we have multiple users writing at the same time? So the next thing that we're planning to do, and we're currently prepping the test cases for this, is, for example, run it over Lustre and look how LNet interferes with each other if you have multiple users writing to the disk. And this is something that cannot be done with current tools. You can only have either the system statistics or the application statistics, but we're hoping to be able to connect it in a meaningful way through this tool.
There's a question in the chat. I would like to know whether you have or could point me toward repositories of HPC application traces, Darshan or others, that include file-level metadata, like file size, number of files accessed, offsets, and so on. I'm currently working on file placement policies in hierarchical storage management systems. These traces are necessary for evaluating my placement strategies.
There should be. I know that they're working on new Darshan logs at some of VS Labs that may be released pretty soon, but I think even Mainz has the HPC IO initiative where they started to collect Darshan traces specifically for popular applications in the European HPC context. I'm not sure if I can find it now in the background, but maybe this is something that would be of interest to you. Let me see. I've never tried to do this on a live call, but yeah, let me know. This is not my project, but this was started by André Brinkmann. They started to collect different Darshan logs specifically for different HPC application traces on different systems. I'm not sure, though, if they include all of the file level metadata. I would have to check.
All right, I have another question. I/O, if we do I/O benchmarking, and no matter if it's application benchmarking or micro benchmarking, is notoriously noisy. So measurements fluctuate like mad. And part of that is, well, at least that's how I imagine it, part of that is the impact of caching. For example, you may be influenced by a job that's just been running before your own job on the cluster node, still dumping its data to the disk. So that's one reason. The other reason is, well, general noise in the system. It can also be that your application has a little load imbalance that may lead to desynchronization effects. So a lot of noise that like waters down the inside. So how do you see the data in the noise? And I don't know if I make myself clear. So doing the experiment twice on different times of the day may get you very different performance data.
That is true. And that's an honestly good question that we're still working on. So there has been some work on I/O jitter, for example, where they just looked at the node level for a parallel application and looked how it varied over different runs on just the node before it even accessed the actual HPC system. So there you have jitter already. But then obviously you do have significant performance variety depending on when you run your job. So we did a little study where we ran the same application for 15 days, twice a day, once in the morning, once in the afternoon on our local machine. And you saw bandwidth fluctuating, IO bandwidth fluctuating between 5.5 gigabyte per second and 6.5 gigabyte per second, just on the same machine. Right now, it is very difficult to identify or pinpoint where this noise is coming from. And we hope We do not have the answer yet, but we have gathered a fairly large group of people being really excited in this topic. So that's already a good start. And we're trying, and that's what we're trying to drive with this explainable I/O. So we're looking at all the different tools. What can they even capture? And then you have noise in the background that you cannot even capture yet, even when it comes from I/O, because they may use a framework that you cannot monitor or profile properly yet. So the answer is right now, it is very, very difficult, but we hope to be able to get a little bit closer to identify and explain fluctuations in the future. And the other unfair thing is, even for I/O operations, even if someone is not doing I/O, but just using the network at the same time to sync data between two compute nodes or different compute nodes of another application run, that will also interfere with your I/O performance. So, yeah.
Okay, last question, rather technical. If you do I/O benchmarking, for example, in order to establish like a performance model for I/O to get the upper limits for bandwidth, for example, and use things like IOR or other I/O benchmarks, do you regularly disable caching to do these measurements? Because if you do, you get proper benchmarks, of course, because you write down to disks right away. On the other hand, that's not the scenario you're observing in practice. In practice, caching is enabled, which means you may see a lot higher bandwidth, a lot lower latency for I/O than you see in these synthetic benchmarks. So my question is, are these synthetic benchmarks with caching disabled useful at all?
They are useful in the sense of being able to give you a clear picture of the raw system performance. So what we do when we run benchmarks is we look at the data sheets and look what should be theoretically possible, which you will never see, obviously. And then we do measurement series with and without caching to observe the performance over time. And then from there, basically derive a time series and to identify system bounds given by caching versus direct I/O. So it can be meaningful in a sense for system benchmarking, but if you're looking into true application behavior, then it would probably not be a representative benchmarking approach.
In your roofline diagrams, that would mean when that caching is enabled, you might observe measurements above the roofline.
We did. We haven't published this yet. We're working on a paper right now that we're hoping to submit in August, where for a very long time we were fairly frustrated because we were trying to profile the actual I/O performance along the edge between a local machine and then an S3 deployment. And we observed data rates for parts of the path that were or I/O bandwidth that was higher than what was actually possible by the technology underneath, meaning the network technology. And it all came down to the way data is being cached and accessed. And yeah, definitely, if you use caching, you see very different effects when it comes to bandwidth. It was basically outside of your roofline model, way outside of your roofline.